high temperatures. At high temperatures. At high temperatures. We would like to see what is the behavior of a specific heat at high temperatures. So you can write that we know that e raised power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial, so on and so on. Okay. So on and so on. ठीक है? So, or I can write down this e raised power x expression like this is equal to x. Okay? Now substituting this, value of e raised power x minus 1 is equal to x from 10 in 9. Substituting value of e raised power x minus 1 from equation 10 in equation 9. We get, what we get? We get the total energy is basically equal to 9n. It is equal to 9n. But I have told you yesterday that x max is equal to kT by kT. Yes, kT by h is equal to theta d. But no, it is basically hfd divided by k. hfd divided by k is equal to theta d. Now hfd divided by kt, it is equal to theta d by t. So here it is reciprocal of this thing. So I can write down t by theta d. So this term, the reciprocal of this term is t by theta d, because hfd by kt is theta d by t. We are having here kt by hfd. This is reciprocal of it. So I can write down then t by theta d ka whole cube. T by theta d ka whole cube, and you are having kt. Kt is there. Okay. Then in the integral you are having 0 theta d by t. Theta d by t. It is x cube by, this is equal to x dx.
Yes, sir.
So 1 and 1 will go. So what will be your total energy expression? It is 9n. T by theta d ka whole cube kt into 0 to theta d by t, 0 to theta d by t, x square dx. X square dx. Now we have to only integrate this part. So I can write down it here. Now your internal energy U is equal to 9n. 9n. It is T by theta d ka whole cube. T by theta d ka whole cube. kt. It is x cube by 3. But x cube by 3 is, the limits are theta d by t and 0. Theta d by t and 0. This is the integration of x square dx. It is x cube by 3. So that means your total energy U is equal to 9n. It will be 3n. Because this 3 and this 9 will go. Okay? You will be having T by theta d ka whole cube. Kt is obviously here. And you are having theta d by t ka whole cube. Theta d by t ka whole cube. Are you getting? Are you following the steps? So that means we were successful in obtaining the value of total energy. Once you get the value of total energy, that means it is easy for us to get the specific heat. What will be the specific heat now? Specific heat CV will be now the differentiation of total energy with temperature. It is d by dt of, what is your U? U is 3n. U is 3n kt k 3n kt, and there is, see, this and this will go.
Yes.
This and this will go.
Yeah, T.
T by theta d by t cube.
KT is equal to R.
KT, yes, NK is equal to R. So you are having this much after. That means 3 NK you will take out. It is basically dt by dt. That is 1. So you are getting result 3 NK. But this 3 NK is, because NK is R. NK is R. So what is this value now? See, we were successful in obtaining the specific heat using Debay model assumptions. Those assumptions were the coupled harmonic oscillators. Okay? And one mode of frequency of one mode of vibration is different from the frequency of other mode of vibration. And the number of modes of vibration are limited in number. Okay? With these, and we have taken both the transverse and the longitudinal waves into consideration. With the help of these, we were successful in obtaining the specific heat at high temperatures. It is again 3R. What is 3R? It is constant. 3R is, that means at high temperature, there will be no change in specific heat. There will be no change in it will having a constant curve. If it is rising like this, you plot a graph versus U versus T, it is rising, then you will be having the constant. So specific heat, CV is constant. CV is constant at high temperatures, and its value is equal to 3R. Its value is equal to 3R, which is again completely in agreement with Dulong-Petit's law. Dulong-Petit's or classical law. See, if you imagine, this classical law was given much earlier, but the complete theory was had not been obtained till the Debay has given his assumptions. On the basis of his assumptions, he has theoretically predicted the behavior of specific heat, which is totally in agreement with the experimental results. This is how we got the result for specific heat at high temperatures. Now we have to get the result for high temperatures. Shall I have it? This is at high temperature. This is at high temperature. Now, what result should we get at low temperatures? Shall I have it? Okay. Those who are coming late, please don't make any noise. You are already entering very late in the class. So then you start disturbing the whole class. So see, at low temperature, case second, at low temperatures, that means at low temperatures T is turning towards 0. So behavior of the temperature is approaching towards it. It may not be 0. It may be 1.999 or 0.999. Okay? Or 0.000000001. But it is not 0. The behavior is towards 0. The tendency is towards 0. That's what limit is suggesting us. So, if the temperature is low, that means its behavior is towards 0. What will happen to theta d by t? It will become infinite. It will become infinite. So how our result will take place? So we were having the equation U is equal to 9n. 9n, it was theta d by t by theta d. T by theta d ka whole cube, because h of d by kt is equal to theta d by t. So inverse of it will be t by theta d. T by theta d, and you are having again the kt is there. Then you are having another factor. So limits will now get changed. Yes, as t tends to 0, theta d by t is approaching towards infinity. So here the upper limit of the integral is now infinity. Upper limit of the integral is now infinity. So you are having here x cube by e raised power x minus 1 dx. If you remember this, you have already solved this integral or used this integral in your statistical mechanics. where you often use this integral. So this integral is basically a standard integral. It's a standard integral. It is a standard integral. We know standard integral 0 to infinity x cubed by e raised power x minus 1 dx is equal to pi 4 by 15. Pi 4 by 15. Pi 4 by 15. See, there are two terms. One is like this. This is just like you are having summation of the terms, you are having the product of the terms. Other symbol is here pi, whose value is 22 by 7. Circumference by diameter of the circle. We are getting the value of pi from there, no? So this is a well-known standard integral. Its value we know it is equal to pi 4 by 15. Now can you solve it now? So your u is equal to 9n. 9n. I will be writing down here 1 by theta d ka whole cube. 1 by theta d ka whole cube. Then you will be having t cube. I will take out t cube and this t will become t4. It will become t4. And you are having obviously the k. 9nk. 9nk 1 by theta d ka cube t4, and for standard integral you are having pi 4 by 15. So your result will turn out to be 9 or it will be 3 5. Okay, it will be 3 or nk is equal to r. We know nk is equal to r. 3 or 3 or 3 or 3 or pi 4, 3 r by 5, 3 r by 5, 3 by 5 r pi 4 by theta d cube into t cube into t4 into t4. Now this is the expression for internal energy, total energy. This is the expression for the total energy. This is the expression for the total energy of the system. So what will be the specific heat then?
du divided.
What will be the specific heat?
Du divided by dt.
Yes, your specific heat is always du by dt. Du by dt. Du by dt. It is equal to d by dt of what is u? What is u? 3 by 5, 3 by 5 or pi 4 by theta d cube into t4 into t4. See, if you look at these terms, this is constant 3 by 5.
Yes, sir.
3 is constant, 5 is constant. Ratio of two constant is always a constant. R is constant, pi is constant, and theta d is as well constant. Theta is the maximum Debay frequency that we are having. So theta d is always also constant. The only variable term is temperature, T4. So you can write down Cv is equal to 3 by 5 or pi 4 theta d cube into, now you are having d by dt of T4. So you can, what is the differentiation of T4? 40 cube. 40 cube. So it will become 12, 3, which this is 3 by 5. 3 by 5. 12 by 5 or was here. 12 by 5 or, that is pi, 12 by I or 12 by 5 or pi 4 by theta d cube into t cube. This is all these terms are basically constant. That means Cv is proportional to t cube. That is known as Debay cube law. That is known as Debay cube law. This equation, names that equation 11. Equation 11 is known as Debay cube law. Debay PQ law. That means the behavior of the specific heat varies as cube of temperature. Varies as, but at what temperature? When T is approaching towards zero, at low temperatures. When temperatures of the system or solid you are taking into consideration is very low, at that time, Debay, based on his assumptions, the assumptions I have so many times told you, based on those assumptions, he has found that the specific heat actually it is not exponentially decreasing as was given by the Einstein. Einstein has given the expression e raised to power minus theta e by t. So it is not very decreasing exponentially, but rather it is varying as cube of temperature. It is varying as cube of temperature. If you perform an experiment on specific heat of solids, you will get the exact result experimentally what has given by the Debay. That means Debay's model was confirmed by experimental observations. That way this theory is now complete. This is the ultimate theory for specific heats that was given by Debay model. So now we are having another topic that I will be taking today, that is what are latest vibrations. Hey you guy, the wearing specs, do you have any problem? Now why you are talking? Why you are better talking? So what are the assumptions of Debay model? Please tell me. What are the assumptions of Debay? You please tell me what are the assumptions of Debay model? We have concluded now the Debay model. Can you tell me what were the assumptions on the basis of which Debay model has been formulated? Or latest waves. What are latest waves or latest vibrations? So first thing that we know that instead of describing the individual motion of electrons, of atoms, individual motion of atoms, their collective motion is considered. In a crystal, which is basically a spatially ordered crystal. When we talk of the spatially ordered, what do we mean by that? Kamran, what do we mean by spatially ordered? When we say spatially ordered crystal, what do we mean by that? No, what do we mean by spatial? S-P-A-T-I-A-L. It is a three-dimensional system. So basically, if you are having some crystal, in a crystal, we are basically not interested in describing the individual motion of atoms. But we try to investigate, we try to find out, we try to solve the problem of these vibrations by taking their collective behavior, or collective motion. That motion once generated, you will get what you call a spatially ordered crystal. Spatially ordered crystal means the arrangement is ordered but in three dimensions. That's what we call as specially ordered crystal. Such collective, I can say, such collective motions of atoms of a crystal, such a collective motion of crystal is known as normal modus of lattice. We call it as normal modus of lattice. We call it as normal modus of lattice. And third thing that we know that a crystal consists of regular arrangement of atoms. A crystal consists of regular arrangement of atoms, okay? But what happens to this regular arrangement of atoms at absolute zero? At absolute zero Kelvin, these atoms occupy their equilibrium positions. Because the motion will start, the motion will be observed, the atoms will oscillate if you are providing some energy to the atoms to oscillate. So when at absolute zero, you cannot provide any energy to the atoms so that they can oscillate. So at absolute zero, they always retain their equilibrium position. So at absolute zero temperature or absolute temperature, at absolute temperature, the atoms occupy their mean or equilibrium position. Mean or equilibrium position. So their existence. See, you are having a continuous neighboring atoms as well. Suppose you take one atom, it will be having neighbor on this side and neighbor on this side. So that means these atoms oscillate. These atoms will definitely oscillate. They will be having both force of attraction or force of repulsion with its nearest neighbors. So their existence, so I can write down their existence force of attraction or repulsion between the nearest neighbors. That means what you interpret from it. If your atom is related, it is dependent on its nearest neighbors, what does it mean? Your atom within the crystal, you are having 5 atoms, it is dependent on its nearest neighbors. What does it signify? It signifies that the motion or the movement is not restricted to a single atom, but whole of a crystal. So that means the vibrations which are not restricted to a single atom, but of a whole crystal, these are known as lattice vibrations. So I can write down therefore the vibrations are not restricted to a single atom, but whole of a crystal. Such vibrations are called lattice vibrations. So now you understood what are lattice vibrations. See why I have taken the topic of latest vibrations, because I have to take a very important concept, that is monoatomic one-dimensional lattice. One-dimensional vibrations or lattice vibrations in one-dimensional monoatomic lattice. Okay, I have to obtain the dispersion relation later, but to have understanding of this concept, it was very important first to understand what are lattice waves. What are lattice waves? So let us move to the very, very important question from the examination point of view. So, latest vibration in one dimensional monoatomic lattice. What do we mean by monoatomic lattice? What do we mean by monoatomic lattice? Huh? What do we mean by monoatomic lattice? Single atom. A lattice where you are having a single atom. Okay? So, this model is based on two assumptions. This model is based on two assumptions. So this model is based on two assumptions. The first assumption is that the atoms are located at equilibrium position. Equilibrium positions in a crystal. And second important assumption on the basis of which this model was formulated is that it oscillates about their mean position with an amplitude less than it is interatomic space. This is another important thing. Another important thing is that it oscillates about, that means the atoms oscillate about their mean position with an amplitude less than it is interatomic space. These are two important things on the basis of which this model has been formulated. It has been derived or solved. Okay? Now we take into consideration a monoatomic lattice. That means the lattice where you are the lattice points or the bases, that means the atoms are of single atom. Okay? So we take, shall I rub this? Consider a monoatomic lattice. Consider a monoatomic lattice. Consisting of identical equidistant atoms having mass m and interatomic space in A. and interatomic spacing A. A is the interatomic spacing and M is the most, because all the atoms are having the same mass. That's why I have written here identical and equidistant. They are arranged within the lattice or within the crystal in such a way that the distance between the atoms is same, that is A. Between 1 and 2, 2 and 3, 3 and 4, the spacing between, the distance between the two atoms is always A. That means they are equidistant. They are equidistant. So these atoms, it is presumed, I am using the word, it is presumed that these atoms are connected by a spring. By a spring. So these atoms are basically held together by springs. They are held together by, why springs? Why you are taking this assumption? Because you have taken into consideration the vibrations, elastic vibrations, or latest vibrations. So in latest vibrations, you must obey Hooke's law. Hooke's law must be obeyed. And the displacement, that means, and the displacement must be within the limits of Hooke's law, within the Hooke's law limits. Within the Hooke's law limits. Hooke's law limits. Basically, you are discussing the elasticity. Once the atoms oscillate within the atoms, they are having some sort of elastic behavior. They are having some sort of elastic behavior. We are not discussing about the plastic behavior or shockwave behavior. We are discussing about the elastic behavior. They are obeying the elastic behavior or elastic waves or latest vibrations. These all obey the displacement which takes place. They must be within the elastic Hooke's law limits. That is, once the atom is displaced, it should come again back to its original position. It should come back to its original position. So the displacement must be within the Hooke's law limits. And an important thing is that only the nearest neighbor interactions are considered. Nearest neighbor interactions are considered. You cannot consider the interactions within the whole system. See, then your problem will become a many-body problem. To solve a many-body problem, you have very huge mathematics. You cannot solve this so easily. That is why we are restricting, with the help of this model, we are only restricting the interaction between its nearest neighbors. With one particle or two particles, you can get the interaction part, the potential part. But if you are having a huge quantity of atoms in a system, there you have to obtain the interaction part. One particle will be having interaction with the other particle. That may in turn will be having interaction to some other particle which is bound to the system. So that way the problem becomes very, very complicated. So that's why the model puts a restriction only between the nearest neighbors. The interaction is taken into consideration only between the nearest neighbors. And another thing is that when the lattice is set into vibration, so both the vibrations are generated, they are either parallel or perpendicular to the propagation vector. So once you set these atoms into vibration, either the vibrations are perpendicular or parallel to the propagation vectors, direction of the propagation vector. Okay? So these are the what you call the assumptions on the basis of which we discuss what you call the mode of atomic lattice in one dimension. I'll be carrying on for 2 more weeks. Okay? I'll not stop here. Now consider a figure. So before considering the figure, we will take only the elastic longitudinal waves. We will only consider elastic longitudinal waves. Elastic longitudinal waves. So the above description that I have written here can be expressed or explained with the help of a diagram that will be drawn on the board. So I am writing this way. So one is a hollow circle, empty circle, another is a blue dot, another is a, then again hollow circle, then blue dot. Then again hollow circle, then blue dot. Again hollow circle, then blue dot. If this is nth particle, if this is nth particle, see first this is n minus 1, this is n plus 1, this is n minus 1. So first what we have said, see these are the particles in the, this is particle, this is particle, this is particle and this is particle. The empty circle, I can write down here, empty circles represent equilibrium position of particles. Equilibrium position of atoms. And blue dots represent displaced atoms. Represent as displaced atoms. See, this is the actual equilibrium position of an atom, Xn. One is, its displacement will be Xn. Okay? This is the, how much it can be displaced. It is displaced to this action, again it comes back to its original position. That is how the behavior of oscillating waves or oscillating particles are. This is the particle here, n plus 1 particle. If it is n is 1, 1 plus 1 is 2, this is particle second. So, this is the displacement. To what extent it will get displaced. This is the equilibrium position. Xn is the displacement of nth particle from equilibrium position. Xn plus 1 is the displacement of particle from Xn plus 1 position. Xn minus 1 is the displacement of the particle from n minus this displacement of n minus 1 particle. What is the interatomic spacing? Interatomic spacing is from this to this, it must be A, because I have presumed that, I have given the assumption that they are equidistant identical particles. Equidistant identical particles, and equidistant means same interatomic separation. So that means distance from this is also A. That means distance from this point is also A. So they are equidistant. They are equidistant. Shall I stop here and move further?
Yes, sir.
Further? Okay.